So today we will be focusing mostly on the exams. It's a Q&A session, so there will be a lot of time for you to ask any questions about any topics that we went through. If there is anything that wouldn't be super clear, we can go over that. And also, I compiled like bunch of questions that that might happen and that might occur in the exams inside our Git repo. So the peak 7 slides, at the end of them they contain like a, oh yeah, I should actually share the screen. So our slides, is it on? Yeah, okay. Our slides at the end, I added after the content, I uploaded a newer version where we have a overview of what we will be sort of going through today. And so I cut down the 7 lessons that we had, more or less, into these topics, and then added some really basic example questions of what in theory I can ask in the exams, but also sort of like the topic by topic deconstruction of the classes. So what I will be asking you today is more or less more open-ended. So we will be talking about tricky questions from the domain and sort of trying to figure out if we actually understand the concept behind those things, behind convolutions or something, and what they bring to the models and stuff. While in the final exam, I will kind of try to boil these questions down into something easier to answer. So yeah, actually, yeah, let's start from here then. So for the actual structure of the exam that's following, or the assignments that or the assessments that you will have, there are 2 parts. Let me check questions. Yes, I think so. Yeah, basically, so it's as open as right. So I think it opens on the 12th and then it closes few days in advance. So you will have several days to actually fill this in. I hope this is this is how it works with my bachelor students. I think it will be more or less similar for you guys. That the exam is you can do it once, but you have a lot of time to actually do it. And so, given the fact that we are all stuck in our homes, it is by default sort of open book, because you can always refer to the slides or the internet or anyone sort of yeah, I don't know. It's a test, but these times are a bit difficult for doing tests. So yeah, and I think there will be, yeah, I think it will not run out of time. I think you can open the test and just start doing it, and it will sort of you will submit. You can submit it only once, but you can sort of take as much time as you want when going through it, because I think it opens on the 12th, and then you have several days to actually fill it in. Yeah. Right. So as for the structure of our class, we have sort of 2 elements, two parts for which you will be marked. The first part was the online testing. So this includes all the Moodle quizzes we added over the class, so over the weeks. This includes all the sort of theoretical questions I was dropping there every now and then, or the practical questions where I wanted you to try some code and maybe submit some result or something. I was going through most of this, so I think, yeah, I realized there are some tests which I have not marked yet, but I think most of it is there. And my marking scheme was always sort of not necessarily binary, but if I saw that you put some work into it, I was mostly trying to give you good marks from that. Whereas if you were missing it, there was nothing. So from that, that will sort of build the first part, and that's actually finished now. This includes the assignment from Rebecca. I have to sort of get in touch with her and get her evaluations, and then I will feed it everything from there in. The second part will be fully, it is still fully open. That's the quiz that we will have next week. There will be sort of two sections in that quiz. First one will be from 20 multiple choice questions. So I will write down the specifics. I think like one way would be that there is always one correct correct answer for each question. Another one would be that it might be slightly more open. I don't know which one I will select, but it will be more or less easier because you will be always. It will be possible for you to sort of eliminate some choices and then choose the one which you think is the most correct. Yeah. So that's the first sort of part. The second will be 3 more or less open-ended questions. So there will be some short essay answers. So in the second part, you can sort of expect something like describing a particular method that we talked about. So maybe some of these techniques, or maybe some concept about one type or the other type of the models. And so that one will be open-ended. There is no sort of right or wrong there. So I will be trying to go through all of that and analyze it sort of bit by bit. And yeah, I guess like if I see that you put enough work in it, I will try to give you good marks, of course. Okay. So that would be these two elements. Roughly speaking, in our class, we went through these 7 topics. The first class is just basically introduction and motivation. There is not much going from there. Then we sort of introduced the fully connected neural networks and also like the neuron as a unit and some talks about parameters and stuff like that, right? And then we talked about convolutional neural networks and sort of what that means for a what specifically can the convolutional neural networks do, how they can sort of divide these well, almost like content and style, but like how they can divide some parts in the design. Then there was the class with interactive ML. I don't have any particular questions here. I think, yeah, I can probably ask Rebecca, and if she has some questions to suggest, I can add them in, but maybe there will be not that much from that part. And then finally, we will go into the generative models area, where this is the generative models 1, the generative models 2. So it's roughly about, again, like talking about the topics and what does it mean for the model to be generating something. And then finally, even the class that you had today in the morning will be included there as well a little bit. So some questions about sequential modeling can also appear. Okay. Right. All of that sounds clear and good. And am I recording everything as well? Yes, hopefully. Okay. Cool. So how it will be today is that I will go one by one with these questions, and I will try to sort of work with you guys who are here online today, and I will be asking some of you who like know the answers to give me some possible answer for those questions. And so we will sort of try some of these questions out, and for you it's a place where you can try out if you understand that question, if your answer is something that I would be that I consider correct, and for those who don't really know if that's you don't really know the correct answer for that question, you can hear your classmates talk about it, or if no one sort of knows, I will sort of be adding some details for all of this. So yeah, hopefully that sounds okay. It will be less organized and less sort of less organized than usual, but I think as a product you will be able to have like a log recording of a session where you can use that to sort of study those topics afterwards, hopefully. Okay, all good? Hopefully. I don't hear any sort of anyone saying that not, so I'm considering it that everything is accepted. Okay, awesome. That's awesome. Okay, so let's start with the first class, or the first big topic that we had, and I guess this is a demo question, right? Because we never really went too deep into anything in the first class. It was like just going, yeah, it was a motivational class. However, we did open up the question about linear regression models. So would someone want to describe to me what is a linear regression model?
I mean, I'm happy to have a go.
Yeah.
So, is it kind of plotting an arbitrary line to a set of data, measuring the error through. I mean, I guess there's a number of different ways of doing it, but what we looked at was mean squared error. And over time, trying to reduce that error so that the line plots the data better.
Okay. And so what would be the error specifically between sort of which points you would be getting those? But yeah, what would you be comparing with the minimal square error or something? Yeah.
It's kind of the average distance to that line.
Yep.
Yeah, so the best fitting line would have the least overall distance for all the data given.
So very good. Let's see, plots a line with okay, so we can call the M and the B the parameters. So I was trying to make a point that that we have a model which is like anything that we can sort of try to fit somehow, and we have some set of parameters that we are changing, and the M and B in this case is the set of parameters.
Yeah.
Okay. So if you have this model trained, how can you use it? I guess is the follow-up question for that.
Yeah, I mean, as Stu says, once you have the function for a line, you can use it the other way around. You can give it give it an X and it'll give you the Y. You'll give it something and it'll give you, I don't know, a label.
Yeah. So what I'm trying to sort of get at is that you could either look in between the data that you had to sort of get some values in the middle of the points, sort of interpolate between points or between data values, or you could use it to sort of widely extrapolate. And so sort of extrapolation means looking sort of further, so somewhere where we didn't have any data for it. Yeah, so maybe this is a good one. So interpolating, we would be getting the answer somewhere here, whereas extrapolating would be sort of trying to predict the value maybe in like the future or the past or something. Okay. Do you see any problems with the linear regression model? Do you see any moment where it can sort of fail? So maybe like, can you see a domain of data where this wouldn't really work?
I mean, is it kind of in terms of like the dimensionality of the data? Is it only good for kind of low dimensional data?
So we worked with 2D points. I think I don't know, maybe. Yeah, I was trying to get into the fact that linear regression can sort of map only a linear dependency. So if there is something like the plots that we have been seeing these days a lot, what is it? The exponential data or something. So if the data has some distribution inside it, which is not linear, data linear regression, I guess, then it would fail basically because like it's useful to map some linear relation in the data, but like if we are trying to plot something like this, the line is not going to be perfect. On average, it will be working. Maybe this. So it will be more or less working on the average, but other models, other types of models would work much better. Yeah, like if you're trying to plot a line through this, you would get a line which is more or less like averagely bad everywhere, but it's not the best for the data. Okay. Yeah. So if we have, you mean like if it's just ints and sort of all the data has been rounded to some discrete blocks, I guess. Yeah. Yeah, because the line that you would be getting is outputting a float value, so you would be getting sort of strange behavior between what you are predicting versus what was your input data. Okay, well, yeah, so this is just like a basic, simple. I don't think that we will have too much from there, honestly. Okay, there was a question I wanted to answer. If you don't use a specific terminology but still attempt to answer it, did you get points? So yes, basically, yeah, you will get points if you will describe something with any sort of terminology, if I get it, if it's correct as well. If you use the terminology, that's bonus because I will be it will be clearer for me to understand what you mean, but I will try to sort of get the idea that you're writing down there anyway. And honestly, it will be like 20 questions, which will be fixed, right? Because it's the multiple question types of questions, multiple answer type of question. So in there, you sort of just will choose the closest answer. I think the only moment where you have to sort of worry about this is the open-ended essay questions. And then, yeah, I will try to be open-minded for your answers as well. And, yeah. Okay, cool. That would be linear regression. Yeah, I'm still figuring that out. I will see this when I am making the questions. So I wrote down the categories and I'm testing the categories today, sort of, but I didn't write the exact questions yet. So yeah, still on that. Okay, so let's go forward. Oh yeah, okay, this is nicer. Let's go forward. This was just a demo, really. I don't think that there will be too much from linear regression, but it's a good representation of like of different type of models and the terminology that we can use there. Something like having parameters that sort of translates to our domain as well. Okay, so the next class we went through the design of fully connected neural networks. So we started with some neurons. We talked a little bit about some like error functions and distances between, like showing how to plug in image data or something, vectorizing the image into flattening it, and then plugging in a single vector or plugging in a layer of vectors, and then talking a little bit about what is the connectivity in all of that. So how to connect one neuron in one layer to, what does it connect to in the previous layer, for example, if we have the fully connected neural network. So that's one part. And then also, I guess that those are the biggest questions. So let's start with these prepared questions. What about the neuron as a model? For now, a single neuron. What are the parameters of a single neuron?
I mean, kind of the same as a line, but there's a weight and a bias, which I guess is the M and the B, or the gradient and the intercept.
Yeah. So a line. So in linear regression, the demo I was showing in the slides was just two-dimensional. I think in theory you can have a multiple-dimensional hyperline. Wait, does it exist?
Yeah. Okay.
But in neurons, we actually had like a bunch of possible inputs, and all of those had their own weights, right? And all parameters.
Yeah.
So if we if we have a single neuron and a input of 10 values, would you dare to guess how many parameters would we have in that neuron? So
say that again, sorry.
Yeah, I will write it down. One neuron, then inputs. Jesus, typos. Anyway. Wrong one. So yeah, anyone has an answer for this? Yeah.
Yeah, I was going to say
11.
11. Yeah.
Yeah.
And it's by constant C. Do you mean is that the bias?
Yeah. Yeah.
Okay.
So yeah, it's roughly like this slide, right? This V1 plus V. I think I maybe. Yeah. I didn't really explain it that much then because I wanted to sort of just keep it simple. Yeah. Well, I think usually what happens is that the additional bias is added as like as a fixed input of size 1, and so then you have a W0 or something, and then that is the next weight. Okay. Yeah, I mean these are correct, right? These numbers, these values. Okay. Okay. So how do we go from there? How do we go from a single neuron into a fully connected neural network? Would someone want to define a fully connected neural network for me? In lay terms, whatever, basically.
Is it when all sort of consecutive layers of neurons are all connected to each neuron in the previous layer?
Mm-hmm. Yeah.
And that makes it fully connected.
Yeah. Good. So in that case, what we have is we have. See here. We have only the so-called fully connected layers, which is just a set of some amount of neurons, and everything from like every unit in a layer of fully connected neurons is always connected to everything in the previous layer. Okay. So yeah, it was a correct answer. And so in a fully connected neural network, we may have a bunch of layers. How many layers we have is sort of arbitrary. That's sort of on us to design, to choose. Okay. What is the possible danger of having every neuron connected with every value in the previous layer?
I mean, the only thing that springs to mind is overfitting, but I guess that is also depending on the number of neurons in each layer, right?
Mm-hmm. Yeah, but that's on the right sort of direction. Yes. Yeah, exactly. So we have when using fully connected neurons, if we input some like really large image or something, then the amount of parameters will be really high for even just the first layer, and so it will be like millions of parameters or even more. And so these types of networks tend to have problems with overfitting. Yeah, but the direct answer is that we would just have too many parameters, and that's even like hard to train anything. It just sort of follows. Okay, but nonetheless, we still use fully connected layers, and yeah, I will talk about I will ask that in the next topic. Okay, how would we calculate the error between the prediction and the label? And we can start by defining what is a prediction and what is a label if you want as well. You're in your own terms, not like the proper definition or anything. That's not the.
I mean, I'm happy to keep talking, but I'm waiting to see if anyone else wants to.
Yeah.
Give it a go.
Yeah. Yeah. Actually, yeah. So anyone else than those who were already answering, would you like to either write down the answer, or try out the answer, or speak? But why?
I think, if I remember correctly, I think for classification, you would use like 0 and 1, and when you label them, you have to kind of check if it aligns with what you predicted by using 0 and 1.
There is really loud keyboard somewhere in the middle. But yes, I think that's correct. Yeah, we sort of have to mention that these labels are something that we have to encode, sort of choose the way how we represent them. So what we were talking about is the one hot vector encoding, where we have a full-on vector and there is just one value which is set on 1 and then everything else is 0. And the which value we choose to be 1 really depends on the class that this data sample has. So if it's a sample of, it depends on the data set, right? But if we have a sample, if you have a data set of numbers, then the first class would be zeros, let's say. Then the label would be something like this: a vector with zeros, but a 1 with 1 category, the first one. Okay, and so then you were saying that so this is called a label, and that these labels need to align with something that the model is outputting, and that's correct. Exactly what it is. So if we train a model, I don't know if I ever had it here exactly. Maybe no. Okay, so if we train a model, we will, during training we are showing them these numbers here and then these labels here, and we are sort of trying to have that model learn this. And then when using that model, we will have some types of outputs from here. So this model will be giving us some numbers. And so what we need to do is to compare these numbers that it's giving us. Oh, sorry, I think I had something here. Yeah, we have to compare these numbers that it's giving us, these predictions, with the labels that we actually assign it with. So there is a sort of distance function between these two. So if this was just a one number and this was just a one number, then we would be getting a like this minus this. If these are vectors, so something like the 10th dimensional vector that we were using here, so the 10 numbers corresponding to 10 classes, then we have to compare them dimension by dimension. But something similar would still happen here as well. So some like MSE, minimal square error, right? Error. Oops. mean squared error, right? That's the one. So you would be comparing one dimension by one dimension and then squaring that and summing that over the whole difference between the prediction and the label. Okay. Well, and the similarity, it's the same thing as in the scenario of having a line and fitting that line in the linear regression. You want to find a line or a setting for the model, the parameters sort of, that minimize this distance, this error. Okay. Yeah. Okay, I think that's enough for this one. Let's continue for the next topic. That would be the convolutional neural networks. Or if there is some like question in the on anyone's mind, please ask them.
Yeah, I do have a quick question about measuring error. We've come across like a few different optimizers, like Adam being one. Is that would Adam be a means of measuring error, or just optimizing like the I don't know, the backpropagation process? Like what is Adam? Yeah, is that an example of measuring error, or is that something else?
So Adam is one type of an algorithm. So it's the way how to minimize the error. So optimizers are sort of the different algorithms that we choose, and then the specific losses, the specific error function is something completely else. That's the loss function. So the easiest optimizer would be the gradient descent or the stochastic gradient descent. What is this? Oh, I'm looking into API calls, so this will be rubbish. Okay. Anyway, so this is choosing sort of the algorithm, which could be the stochastic gradient descent, or Adam, or RSMprop, and others and others and others. And these are just different ways how to iterate over the parameters, how to set the parameters from some error functions. And the error function is sort of set apart. That's something that we use to measure how the process is going. So there can be, these are two separate things. We will set the function and then sort of play around and select the correct algorithm which would work. Or the other way around also, we can sort of select the one optimizer when we want to use. Maybe we have heard that, I don't know, Adam is really good with for us because it's mostly automatic and it will just figure everything out, whereas stochastic gradient descent is something that we would have to sort of really work hard and find the correct parameters. So we will choose Adam, and then we can sort of play around with the loss function, and then maybe even like use some standard one, or maybe add some changes to it, as we have also seen in like some papers which we were reading, where they were sort of playing around by defining new loss functions. Okay, good question though. Yeah. All right. I think it doesn't matter. It matters in this case. It doesn't matter when you sort of talk about it as a distance function between prediction and label, because they always will be some like squared, and then there will be some. They mostly are absolute. So in that case, they are symmetrical when you. But actually some functions are not symmetrical. Correct. Correct question. So my writing here might be not correct. I meant like a arbitrary distance function between a prediction and a label. So the order here would matter, but if it is squared, then it doesn't really matter, because it's as if it was called like an absolute value from that difference. Okay. So let's continue to the next bit, to the convolutional neural networks, and almost following the questions from the last slide, let's talk about model overfitting. Well, first, what is model overfitting actually?
I try to say something too.
Uh-huh.
I try to say something too. Just that Josh doesn't have to.
Awesome, thanks.
Well, okay. Model overfitting is if the model is too attuned to the training data and doesn't generalize well to data that's beyond that.
Awesome. Yeah, exactly. That's good. Okay. So how can we detect that, and how can we fight against that?
Me as well, or?
Yeah, sure.
Well, I guess you can detect it if the perform, and you usually have like training data and test data, and you can usually detect it if the performance degrades on the test data. Like if you train it too much and then performance goes down, that's usually overfitting. And yeah, we had a couple of techniques of how to prevent that. There's just training less or dropping layers. Like there's a technique where it's not like fully connected, but you drop like some layers with 50% chance. Yeah, basically making it harder to train, so it doesn't overfit. Yeah.
Yep, very good. So there are a lot of techniques. The easier ones would be just like figuring out a correct size of the network. So like very generally speaking, if you have a model which is too big for the data you're trying to learn, to have it learn, it will just be able to memorize everything, and that's the moment where it sort of fails, because it just memorized the whole training data set, and then if you put in anything else, it's sort of just thinking in terms of being able to really like recall, almost like almost as if the whole training data set was saved in there. And that's a problem because the boundaries inside the model become too fragile. I think that was a visualization in our slides where the boundaries of the possible model, I mean, like this can be a decision boundary between two classes, and this is a simplification because it's a 2D plot. But nevertheless, even if it's a hyperdimensional space with many dimensions, you would be getting some. If this boundary is made to be super aligned to the training data, it will be more fragile to any new data coming in. So it no longer is able to generalize, as you were saying. Okay. The techniques that they use, I guess, yeah, roughly speaking, they make it harder for the model to for the model to train on the data. They can also make it. There are some tricks to sort of like train a model on like try to make it that it has to be able to generalize on different sets of data. So you would be splitting the training data into smaller bits and sort of trying, like, forcing it to be able to generalize on the other bits as well. Okay, but yeah, so this is the reason why we would be splitting data into something like training, testing, and even validation data sets. So yeah. Okay, right. Okay, and so just to maybe add like the last detail, a training data set is something that the model actually sees when it's training, but the validation data set is something it never has an access to when training. It's something that we only evaluate the model on. So yeah, there are some occasions where like if you code it wrongly, then you will mix these test and train sets together. This happens to me already, and it can happen sort of. It can pollute your results because then you are training on something that evaluating it on something that you already trained it on. Or it can happen that if you are augmenting your data, you really have to sort of separate those bits again, because if you augment the data and then like add the flipped version of the 0 into your validation dataset, maybe it's still the same 0. So that would be a problem. Okay. Right. So okay, I'm happy with that answer. Let's talk about the sort of main bit that we introduced in the third week, and that would be the convolution operation. What does it do as a filter, sort of? Can you describe it as a filter? So I'm not now speaking about just like general convolution operation, which can be done on anything maybe on images, and not the one that is then plugged into the neural networks. Even like text answer is correct. It's okay to just like write down what you think.
I'll
Okay.
type in again.
Yeah.
I mean, I don't know if I'm going to be using the right terminology necessarily, but like a convolution applies the same. I don't know if transformation would be the right word, but like the same kind of set of operations for each pixel based on the pixels around it. So there's a kernel which is of a given size, say it's like 3 by 3, and then for every pixel in the image, that kernel determines the transformation of that pixel.
So what are some examples of how convolution can be used in, like, what could be done with this? Yeah. Okay. Would you be able to write down a filter for edge detection or sharpening, for example? Or can you imagine how the values for a blur filter would look like, just in general?
I think blur just sums all of the pixel values around it and then averages them.
Okay. Yeah. So yeah, that's correct. So if you have like 3 by 3 filter kernel, you would be okay, yeah, something like this, I think, yeah, because then it's sort of valuing in those things that have the, yeah, it doesn't matter really. But the concept is what matters. It would be getting in the values from like the right side of that kernel minus whatever the values were on the left side. Okay, so this would be a edge detection for like a left to right, I guess, edges.
Incidentally, I have seen that kernels don't necessarily always need to be odd. I read something about that recently. It's easier if they're odd, but they don't necessarily have to be.
Right. Yeah, with convolutions, it's tricky because you are like feeding in a square thing which happens over the image, and especially with the generative models, you then see again and again these like square artifacts happening. So I saw some attempts to use like circular convolutions and stuff like this, but like crazy stuff, which, yeah.
Yeah. Also, I was looking at this something called diluted kernels, where dilated kernels, sorry, where
Yeah,
it's like
donut.
they kind of it's not the immediate neighbors around it. It's kind of you spread it. Yeah, it's quite interesting.
Yeah. And there are some like donut convolutions. I don't know how they are called. Where, yeah, I guess donut inception, normal donut convolution, where you are sort of like forcing it to look at different values. Okay. Before we get too deep into donuts, would you be able to write down a convolutional operation as a math operation or as a function where you have like input as the image input on the input side? Yeah, you would have a input of the image, and you would have to output the edited image with a given kernel. I didn't have lunch. I'm not opening this yet. Yeah, would you be able to write that down as a function? I mean, I'm not asking you to write it down here, but like, think about it. Would you be able to recall the operation that happens there and like rewrite it into code?
Yeah, I would have an easier time writing it in code than in math terminology. I think.
Cool. I have a funny, horrible story. I had a long time ago, I had a call with a Google place where I'm happy that I didn't end up with because it would be entirely different path in my life, I guess. But not necessarily a better one. And I had like a fever when I got the call for some interview or something, and they asked me to. I was preparing the whole 2 weeks for like very theoretical, very in-depth questions. I was like, okay, this model is really good for this type of data. This like, if we have hyperdimensional data, it's really hard, but I know the trick to sort of dissociate it and whatever, right? And then they asked me to write down a convolutional operation as a function, and I melted it down. I wasn't able to. I was able to draw it, but never to actually like. Oh my god, this is so basic. I don't know. So yeah, convolution operation is a good thing to sort of practice for a interview calls. Just by the way.
Interesting.
Yeah, terrible, horrible memory. Okay. Given a let's say 5x5 convolution, a 5x5 kernel of a convolution, if we apply it on a 2 to 4 by 2 to 4 image, and let's say that we have sort of like we add some padding so it evaluates into a correct image to like produce a 2 to 4 by 2 to 4 image. How many parameters would we get for a single kernel operation or certain convolution operation?
Is that assuming that we're not padding the image?
I mean, we are padding it so that the dimension remains the same. But we sort of, that's automatic. We don't have to include it into this answer.
Oh, yeah.
So how many parameters would there be in a 5x5 convolution? Yep, exactly. And so the reason is that the convolution, like this is a 3x3 one, but this is a single filter of which has these numbers, so it could be something like this, right? And so this is these are the values, and this same filter is then repeated over and over the image. So the trick there, I guess, is that we are reusing the same 9 numbers, the same 9 weights over the whole image. Okay, and so the one difference that I can be asking about I can be asking about a difference between fully connected and convolutional neural networks. One difference there would be the amount of parameters, right? That's the sort of high conceptual difference there, because one of them has a 9 values for a image to image transformation, while the other one would have I think I even showed it here somewhere, like a lot of parameters just for plugging in a single image by a single neuron. So that is one thing to sort of remember. So we talked a little bit about zero padding. What is it and why would we use it?
Say that question again, sorry. I
right.
cut out for
Oh, sorry. So what about zero padding? What is zero padding used for, and why do we? What is it used for? What is used for?
To kind of extend the dimension of the image so that you get the same dimension output as you give it an input.
Mm-hmm. Yep.
That makes sense. So if there was no padding, then the kernel would start in the corner, and you'd lose some data because the center of the kernel is not at the very edge of the image.
Mm-hmm. Exactly. So you would be getting, like, you could even calculate it how many, how much you would lose, for example, in 5x5 kernel, right? if we didn't have zero padding here with a 5x5 kernel, how much would be the output? For example,
I mean, yeah, you'd lose the first two rows and first two columns, and then the last two columns.
Yeah. Great. Awesome. So one more thing that, for some reason, I think like convolutions are the thing that's easy to ask about in like interview calls. So another interview, another time, another path. I was asked about stacking convolutions after each other and sort of trying to figure out what happens if you have a 3x3 convolution. Learn to write first, yep. And then another 3x3 convolution. So if this happens, you have stack of two convolutions, and then you look at one pixel of that final, like after this final transformation. How large is the domain or the number of pixels that this would be actually covering in the original image? What would be the? I'm trying to figure out the name. No. Yeah. So after these two translations, we are getting another image, right? With zero padding or without, it doesn't really matter. But yeah, if we have one pixel at the end, what would be the reach of that one pixel? Where would it be getting information from in the original image?
So the image has gone through two 3x3 convolutions.
Yep.
So you would have lost 4 pixels of in the x and y. I'm not 100% sure.
Yeah, me neither. I have to write it down. Sorry. Let's see. Okay. Yeah. Right. I think I have.
Is it 5x5?
Yes. Yeah. It should be 5x5.
Yeah. Okay. Cool.
Yep. Cool. Because if we look at we sort of have to unroll it, right? Because like from one pixel we would be getting 3x3 area, and then for every pixel in that 3x3 area, we are again like including a 3x3 area, and so I don't know how to share this. I was drawing it on a paper. We would be getting a in total 5x5 area. Let's see, maybe someone did this. Okay, I think it's called a receptive field. The way how. Okay, yeah, this is exactly what I was showing then. So, let me. So it's called a receptive field, which means the number of pixels the one target pixel sort of captures or gets the information from. So if the first pixel had 3x3 region, then every pixel in this in the second sort of layer would be also getting 3x3. So this one has these 3, the next one would be covering these 3, and the last one would be covering this last bit. And so from the middle one we are getting 3x3, bless you, and then from these two side ones we are getting only one new information. Okay, so yeah, this is sort of yeah, I think it's useful to know. Maybe it's too much. Like I don't want you to be counting during the exams, but I still wanted you to sort of have that knowledge. Yeah, because again, this was something I was asked during an interview. Okay, so let's move on from that. Let's move on from convolutions a little bit. So what allows different layers inside the CNN convolutional neural network to specialize. And by specialize, I mean that maybe, as you remember from the class, some of the layers will remember sort of very detailed information, while some other layers will remember more or less the conceptual information. So what's the content inside the image, while some of the other ones would be sort of focusing on the really nearby areas of like edges, texture, information, colors, stuff like this. What would be what allows this design of convolutional neural networks to have this specialization?
I guess the fact that you have many consecutive layers.
Mm-hmm. Yeah. So actually, probably that would be enough, because if we have this, right, then we can see that this one pixel has been mapped on a much larger area. There is one more thing that sort of helps with this, if you remember from the class, which even more sort of increases the range of the receptive field of that pixel, or of that one information in the final output.
Is it the pooling layers?
Yes, exactly. Okay. So what I'm asking here is basically for the convolutional to pooling combo. So the repeating of convolutions and poolings. And so what could you describe that then? The convolutions and pooling, how they work?
So I guess the convolution kind of, it reduces, I don't know, it's hard to put it into words. I can picture the diagram, and it kind of, I know that it it's kind of stacks these layers on top of one another, so the dimensionality changes.
Mm-hmm. So what does the pooling layer do actually? Just simply start with that.
I guess just combines all of the results of the convolutions.
I think
on top of one another. Yeah.
In the AlexNet paper, they used the max pooling, which is like you also apply this like filter of certain dimension, and then you just sort of grab the maximum value within that kernel, or it's not kernel, but in that area, and then you apply that to each of the
so
pixels.
I guess I didn't get that answer here. The important point is that the pooling operation reduces the dimension of the like sort of just downscales the image. So if this is very similar to some like Photoshop operation or something, where you would get a image here, and then you would call a Control-Alt-I and then reduce it by 50%, and then so this is something that the pooling does. It just downsamples it by half, basically. And then there are these fancy operations of like max pooling, where besides there are different ways how to downscale an image, right? But like max pooling would be looking at the max value from these 2x2, like 4 pixels, and always reducing that one to 1 pixel. Bless you. But okay, so that is what you were saying is correct, basically, because it is somehow combining the information, but the important bit there is that it reduces the resolution. And so when the later layers, the later convolutions work on even if it's 3x3, and this is again 3x3, then just by looking at the image before the pooling, this 3x3 region corresponded to a 6x6 region. So this pooling operation very rapidly sort of increases the receptive field of this convolution, right? Does that make sense?
Yeah.
Okay, cool. Yeah. Okay, and so one thing, I mean, what you were saying is also correct. The fact that we are even repeating convolutions, they have these even just by repeating them, right, we would be getting larger and larger receptive fields, so the area where we are getting the information from. But even to add to this, we are sort of adding the pooling layer, which is increasing that even more rapidly. Cool. And so the last question for the convolution and neural networks. If you remember, somewhere at the end of that class, we were talking about the architecture design for all convolutional neural networks, and the fact that they have these 2 bits that we can even separate them and call them names, and sort of talk about them having a specific function. And this distinction was between a feature extractor and a classifier section. Would you be able to either tell me why this happens, why is this division happening, or what these 2 parts are responsible for?
So I mean, I guess the convolutional layers are the feature extraction, right? And they're fundamentally, are they kind of about reducing the dimensionality of the data? And then the classifier section would be when it starts to become like these fully connected layers, and I presume they can work with lower dimensional data a bit easier and more efficiently. Is that kind of why the convolutions lead into these fully connected layers to then give you some sort of prediction, or whatever it is that the model's doing?
Yeah. I don't know if they would be. So I think the reason why we have one, like the simplest reason is that we are by these convolutions and poolings at the start, we are just reducing the image from like 224 by 224 by 3, which is a lot of values, into something which is more manageable. So some, I don't know, it depends on the design, right? But we would have like 8 by 8, the resolution after several pooling layers, for example, and then maybe still 32 channels for the convolutions that we chose, or something more. I don't remember what they used in the AnnexNet, but it would be a reduced amount. And then if we connect the fully connected layers after that, then the number of parameters then would be lower than just connecting it at the start. Okay, but at the same time, it's also just separating the functionality more or less as you are saying. So the convolutional layers at the start, they are sort of processing it as if it were different filters. So they are trying to figure out what is the important bits from the information we are giving it, and extract that into some smaller representation, sort of almost compress it, right? And in theory, we could even call some different types of networks as a feature extractor. If at the end we are getting some small feature, then it's a feature extractor for all we care. But specifically in the convolutional neural networks, this separation happens at the edge where we are using the convolutions and the fully connected layers. Yeah, basically as you were both saying. Okay. About the purpose of these 2 sections, yeah, I think you were also correct. One of them compresses or extracts the relevant feature information, while the other one brings that abstracted feature representation into a classification. Why it happens? I guess it happens because of the design of the network, because we are really forcing it to sort of reduce the information in the feature extracting section, so really compress it. Like we are forcing it to downsample that input image into some smaller representation in the middle, and then the fully connected layers are working better when then connecting to a classifier section. I mean, into the late classification at the end of the model. I guess you could even call practically speaking, I don't know if the frames from AlexNet are here. Yeah. So we have been working with with features even somewhere in the middle of this, right? So in theory, strictly speaking, these two layers are the fully connected ones. So this would be the classifier, and then all of this would be the feature extractor. But in theory, we can also talk about this being the feature extractor, more or less. But these features are sort of less higher dimensional one, less conceptual ones, but more still focusing on the details. This is the track of what actually even the previous question was asking about, the specialization of convolutions. And also the same way we could use vectors from this moment, or even this moment, to sort of describe the vector of the to use that as the feature for some other applications. Yeah. Okay. Right. I hope that cleared it a little bit. Okay. So before we go into the next bit, which are these three sections, the generative models, and later some sequential models, I think we should have a pause now. And yeah, we will continue with these. Let's have a 20-minute pause, and which means that 12. Wait, it will be UK time 13, I think, right? 13:10 of UK time. So in the meantime, you can think of, like, if there's some questions in these about these topics, something not clear. Oh yes, yeah, that's correct. Yeah, we can talk about that later as well. That's a good question, actually. This bit. Okay. Let's talk after the post then. After the pause. Okay, so there are some questions. If there will be coding questions, so in the test, I will not be asking for any like piece of code or for you to write down anything. Yeah, I think it's more important to know how to sort of the concept behind it rather than to know how to exactly write it down. Because I think if you know the concept, then you can get to the state of knowing how to write it down eventually. And also, in theory, the practical part of the marking was supposed to be in the other part of the exam. So yeah, that should be there. Yes, this was one thing to follow up on. Okay, so let's see. Yep, everything is correct. And hopefully everyone is here again. Let's answer one last thing about the convolutional neural networks. Josh was talking about the advantage of convolutional neural networks, that they have a locality, that they maintain spatial relation. Would you like to explain that and sort of answer that question? So to say what it means for the convolutions to maintain locality of the information?
So I mean, I guess like an alternative way to run an image through a machine learning system would be to convert it into a single long vector, right? Mm-hmm. Which I think we saw with one of the examples where they did that with the MNIST data set. Mm-hmm. And then you could just run that through as we do everything else, just into like a series of fully connected layers. But I guess then the issue with that is that, the benefit rather of running it through convolutional layers is that as the data is reduced through the convolutions, it encodes. Oh God! As soon as I try and use words to explain this, I completely lose it. But
I think you're going on the right track. So.
The convolutions, they kind of encode the information surrounding any given pixel in the reduction process. So that's why they can be used for kind of like feature extraction, because the same convolution is appropriate anywhere in the image. But if you converted that image to one big long vector, then you can't perform that same. You can't do the same thing. So, like, if a tennis ball is in the top left of an image, it'll still be the same features would be extracted as if it was in the bottom right of the image.
Yeah, exactly. Well put. The one thing to sort of say is that when going one layer by layer, we sort of maintain the locality. So there are 2 bits for that, right? Like, one thing is that when using the convolutional operation, it has an access to all the nearby pixels. So that's one thing that's important. But the other thing is also that after the operation, the output we have still has the same locality. So still the same things which were more or less next to each other are again next to each other. And so actually that's something that maybe feeds into this part, because at this moment where we use the fully corrected layers, we sort of give up on the locality. We say, okay, it doesn't matter now. We no longer want to really maintain the fact that these things were sort of next to each other, even though they are sort of really abstracted here. The pixel values here are not the real things here, but they somehow do encode the areas of the image. But if you flatten them, exactly as you were saying, you sort of give up on that information. You even tell the model sort of, okay, now forget about that, flatten it, and consider everything really independent. And yeah, that's a huge point actually for using convolutional layers. Yeah, cool. Yeah. Cool. The long repeater notebooks. I agree. They were sometimes hard to use and to write as well. So the reason for the notebooks was, well, I was hoping to sort of give you something that you can then use with some experiments of your own. Because sometimes just talking about this doesn't really show you, like, yeah, this plugs into that. You don't get to see that. Okay, let's talk about the other category, the next bit. And that would be the autoencoders and GANs. So I guess the question I would like to ask is for someone to describe the autoencoder as a identity operation learning, and sort of what I mean by that as well. So you can start by describing what an autoencoder is, but I would like it to be related to the identity operation learning. Any one of you guys who didn't speak much yet can speak up. Or the usual suspects can also speak up. I mean, it's okay.
To be honest, I am a little bit lost with this one because I think I can't really remember how they differ to a convolutional network in terms of their architecture. I know in principle it's about like representing a larger amount of data in terms of a smaller a smaller vector or something that kind of represents more data with less.
What happens at the output of a autoencoder? What is the output supposed to be, actually?
Just lower dimensional, like vector representation of what it's given.
So that's the bottleneck, the middle part, but the output is actually it's supposed to be the same thing as the input. So that's
I see. Okay.
Yeah. So that's the. Let me open it up. Yeah, I mean, like at some moment everything seems to be the same. I get that. We went through them quite fast as well, so that's fine. Here. Okay. So autoencoders work roughly on this sort of. Yeah. See. Yeah. We will get to that as well later. So autoencoders are specific in the way that the input here and the output here, these two images, are supposed to be the same thing. So you are basically trying to force the model to have some sort of convolutional bit here. Of course, there will be some convolutional layers, which convert this into a latent vector representation, which means like a smaller version of that encoded image. So maybe encode a something by something resolution image as a 512 numbers vector. So you are even reducing it from like a 2D information into a single 1D information. But most importantly, you are compressing that information. And then on this second bit, you are trying to reconstruct that information back into its original resolution, but also it's supposed to be the same thing here. So I'm just writing out down a note for myself. Okay, so we can call these bits a encoder and a decoder, and like this is probably helpful to see because this looks entirely like a classification network, but this is sort of undoing that classification. Okay. So which part of this setup can we use as a generative model, and how?
Well, the decoder part can, because you can just feed it any kind of vector which fits that kind of like latent representation size, and it will give you an output.
Yep. Good. Okay.
So the encoder part of the network, that still is essentially, or could be, a convolutional neural network.
Yeah. Basically, so I think I have even seen like autoencoders which don't even have fully connected layers here, so they really all the way work with a fully connected, fully convolutional. Yeah, sure, I can say that as well. Convolutional layers all the way. So somewhere here they would get like 32 by 4 by 4 dimension, and so that this latent representation even is 2D actually, or like it works as an image almost. And then they have a decoder here, which it really works. Like you can then flatten that vector and then reshape into that vector if you need to, sort of when working with that. But I have also seen places where they were using convolutions and poolings and then some fully connected layers, really. So I guess this would be the standard way. Yeah. In the end, whatever works is the thing that you will use. So yeah, it's not as strict, but yeah. Okay. What what can you do with autoencoders that's sort of unique to the other models? Like namely compared with the GAN, the generative adversarial network. I mean, we will talk about it in a bit as well, but like still, what is the thing that is like one of the differences between these two models? Yeah, perfect. So basically, it means that we have at our disposal this bit, this encoder bit, and then we can like take a real sample from somewhere, encode that, and get the latent representation of that real sample. I mean, as we practically saw, like it's not perfect. So when we decode it, the what was it somewhere here? Like the scissor that we remake is rubbish, and so it's and this was a simple model, right? But even with some, I think we used MNIST there as well. Even with some faces or something, you would be getting a reconstruction which is a bit rubbish, but it's a thing that is that we cannot really do with some other models, with GANs, for example, in their default version. Okay, cool. So let's go forward. What about GAN? Could someone describe it as a two-player game? And what I mean by that description, or like what I mean by that question, actually.
Well, in a GAN, you have a generator and a discriminator that are sort of competing with each other to some extent. So the generator is like generating images, and the discriminator is then determining whether those images should belong in the same sort of set of data as the training data. And then the generator becomes sort of becomes better at sort of, I guess, fooling the discriminator.
So could you describe like the way how we would train a GAN system? What would be the steps and how you would iterate over that?
Well, first you I guess you train I don't know if it's like a classification on the discriminator first. So something is or isn't part of the, or like similar to the training data. And then the generator is just, you basically just plug in noise and adjust the parameters. I'm not sure if I know what you're asking.
Yeah, okay.
Sorry.
I don't think it matters really with which one we start. I think practically it must matter, but like for this, just theoretically talking about it, it doesn't. So yeah, the concept is that we are swapping between these two, and yeah, I guess some more details I would like to ask about it. Okay. Yeah. Okay. So one thing to sort of note there in the training process is when training one thing or the other thing, you should like freeze one of them or the other. So that is some amount of detail that we would like to sort of know. So for example, when we are training a discriminator at the start, let's say that this is the starting point. Do we train the generator as well, or is it included in that loop somewhere, or not really? So when training,
train both simultaneously.
So I think like you would have to separate them actually, because when training the discriminator, it's just the it's just the last bit. I jumped somewhere. Yes, so here. So at this moment, we don't have to care about the generator almost at all. I mean, like we would have to generate these images, but this bit is basically frozen. It means that we don't change the values at all there. we basically we wouldn't really care about this if we generated these images in advance, sort of, to have like a sampling from the generator and the real dataset. What about the next step when we are training the generator? What happens with the with this architecture? So maybe are we training when training the generator? Are we changing something on the discriminator as well, or is it frozen?
Oh yeah, it's frozen at that point. Right?
Yeah. Okay.
And you're just inputting the output of the generator into the input of the discriminator, and then getting an output on whether it's real or not.
And at that moment where we are sort of training the generator here, we are, in fact, really what we were saying, we are feeding it all the way through the discriminator and getting this output. And the I guess the important bit is that we are trying to make the discriminator sort of assign it a real sign, even though we are generating them right now. So sort of change the generator in a way that the discriminator will be fooled and it will generate, like it will assign it as a real. And so it's a bit subtle, but what the important bit there is that when using this trading scheme, we are sort of feeding things all the way from here, the vectors generating things, then feeding in the images into here, but we are then propagating the errors all the way from this back. And so at that moment we are sort of getting some gradients are sort of flowing through the networks, are changing the parameters of the generator, but this happens as a way to sort of to fool the discriminator. So these parameter changes are something which is I guess you would say it's really like non-linear, hard things that are changing, that it's not really clear why these parameters would have to be changed in this way to change the image in a way like that, right? So the difference is that the error function here is something which has been propagated all the way from the discriminator. So it's no longer just like looking at these two values and comparing them and then saying, oh yeah, this pixel here versus this pixel here, like the difference is there. Instead of comparing these two, you are comparing things through the discriminator. Okay, so I guess the follow-up question is that does the generator see the real data set at any moment? Like actually has an access to it?
Yeah, I don't think so.
Yep, nope, not really. So it's really like just a magical trick, I guess. I mean, not really, because we are sort of like it's a strange setup for training for sure. Because I think the problem would be that if it had an access to those data, it would just sort of really like just learn the data distribution, and it would just have the same more or less problems with the data as a autoencoder would have, or it could overfit really easily. But because we are sort of doing this magical trick of feeding the information from the real dataset into the discriminator first in this moment, and then sort of having all of that information saved in these weights somewhere in the model, sort of like really represented in some abstract way, and then we are feeding that abstract way or that abstract representation from one model to another. That's really the special trick that sort of will cause the generator to be able to like generate really high quality samples versus something like a autoencoder. Okay, this is me abstractly talking about things. So if I were to ask you again, and sort of like what would be the differences between an autoencoder and a GAN? I guess you already answered them a little bit. One would be the possibility to encode images, and then another. I mean, I don't want you to sort of just tell me what I was saying now, But this loss function is, I'm trying to refer to what I was sort of explaining now, that the, yeah, I guess I can ask it actually. What is the difference when we would be comparing these two images and then training an autoencoder with sort of the, wait, that was a, here. So in here we are comparing these two images, and so that is where the loss comes from. Whereas here we are sort of propagating the information from the real data set into here, and then from here to here in a like two-step manner. What is the actual difference for the data that we generate? What is the kind of qualitative result of this distinction between these two models? Or am I asking a stupid question? I mean, maybe I am.
I guess the autoencoder doesn't really have a data set the same way that a GAN would.
It would be, I mean, it would be still getting like, here there are a bunch of images, right? Like, so here there is not just one, here is a set of images, and the same here. Oops. And but the same thing happens here as well, and in the generated ones as well. So loss of fidelity. Yeah. So basically, in a bit it's said here as well. One difference between these two models is that this one will, because it's, wait, can I make some drawings here? Because it's comparing these two images with a loss function, and this loss function is some like squared error metric. Whereas this one is not really comparing in the domain of images. It's comparing some weird stuff which is somewhere in the generator and the discriminator. This first method is way more prone to having errors, which would be sort of reconstructing the images with these artifacts. So what is created here is a blurry representation. I guess it's basically what Stuart was saying, because you have forced this image to be encoded into a small representation and then sort of reconstructed from there. Nothing really stops the model from just encoding the overall information, for sort of blurring it out, basically. And also it's given with the fact that we are checking a square distance here. So the error is more or less the same for, I mean, the optimal solution for a square distance is an average sort of like solution, right? Like average result will be getting good loss, good loss values from like a square distance. Whereas in here we never kind of measured these two samples together. So we are not getting a square distance error metric. We are getting something which is somewhere encoded inside the network. Okay. Well, so the answer that I would be sort of trying to guess here is that the difference would be that the autoencoder is producing more or less blurry images, while something like a GAN can actually capture some detail, like more details in there. Okay. I mean, I'm getting into more and more abstract fields, so these questions are a bit like, yeah, I don't know. Did it make sense though when I was explaining it here now? More or less. Not at all.
Yeah. It does make sense.
Okay. Yeah. Cool. Okay, and so the last question on this slide. We talked about various GAN designs, where we just described the basic GAN setup. What is the special sauce that they added in the progressively growing GAN? I guess. What is, like, there are maybe more differences with that, right? But what would be the main sort of trick that they are using to achieve really high quality results. Okay. All generative, all papers presenting generative models have shown, like, have used this dirty trick. So cherry picking means that they will just choose the nice looking results rather than showing everything. Well, sure. The biggest difference between a regular gun and a progressively growing gun is the fact that we are increasing the resolution of both the generated and the discriminated images. So I think I have a image about this somewhere. Right? Do you remember this bit a little bit? So they are sort of So they had these, of course, generator and discriminator bit, but they are also adding layer by layer and sort of increasing the this intermediate bit, this bit in the middle. So these two images are worked at with different resolutions. And so this means that when we are training it at this moment, we are sort of really focusing on the overall information, and the detail that needs to be there as well is kind of lifted to this bit some later stages of training. Okay, I mean
does the discriminator in that process, is the data set also reduced to that resolution?
So if you remember a little bit, like we were working with one collab where we were training with a progressively growing gun, and somewhere in the process we had to sort of cook the data set into some files and TF record files, and from one folder of images it created like 10 TF records files, and each one of those files had the whole dataset copied over and over again at different resolutions. So there was the whole dataset with 1000 by 1000, then a whole dataset at 500 by 512, then the whole all the way to like 4x4, which is crazy. It's so wasteful in terms of space, but then it's fast to sort of access that information. Oh yes, and also they encode it with like no raw pixel values. So I guess that's the reason why like it then can be loaded into a GPU fast, because you just copy it somewhere in memory, but you don't have to uncompress it. But still, it's horrible. It's like you have 100 gigabytes from just one simple like dataset. Yeah. Okay. Okay. Some questions about the autoencoders and guns. I figured out one more question, I guess. So, this one. Can someone explain to me what do I mean by telling you the visual attribute vectors? So what does a visual attribute mean in a dataset, and how can I get a vector of that?
I mean, is it the vector representation of an image?
So
It's in like something from the vector representation in the latent space, or
yes,
like a latent vector.
yeah. So it's some sort of like latent space arithmetics bit, but it was a specific example when if we had a data set full of labels with labeled data, we were sort of able to cluster bunch of that data into one sort of cluster, one blob somewhere in the hyperspace, and then another blob of like samples in the other part of the hyperspace, and then sort of compare these two clusters, these two blobs in that space. And that would happen when, for example, these two blobs would be created by samples from which they have one specific attribute, and then the other one wouldn't have. So this sounds really massive right now, but what that means is more or less this. So being able to encode data, which is maybe images without a smile, without one category, and then images with that smile, with that category. And in here, it's one-to-one correspondence between the people, but in theory, it doesn't have to be, right? It could be also just samples from one domain and samples from another domain. And then at that moment, you would be able to do tricks like this. You would be able to learn what a smile vector looks like, what a visual attribute for a smile looks like, and then add in that vector to anything else. So you can sort of I think this was frozen. So you could be slowly moving that sample in the latent space in the direction that you figured out that, hey, this direction corresponds to smiling. And so this is also the way how people like Mario Klingerman were sort of messing around with the faces, because they were sort of mapping some like music sound, the beat or something into like opened eyes vectors or something, and so it looks strange, right? But then so that would be what I was sort of meaning with visual attribute vectors. Okay, good. And I'm slowly feeding in or adding in some new questions. What about some ways how to interact with GANs and autoencoders? What are the, I guess maybe the first things that would come to your mind when talking about interaction with GANs and autoencoders? Let's say that we have these trained models, and then we want to like create an application somewhere, and we want to maybe allow the user to interact with it, or
I guess by sampling that latent space using these kind of visual attribute vectors in different ways, so you can like interpolate between 2 points in this kind of hyperspace, or I don't know, I guess explore these kind of clusterings.
Yeah, so that would be the GAN interaction, basically what you were saying, and also what was Stuart was saying. And with autoencoders, there is sort of one additional bit where you can encode real samples. So you can, oops, no, where is it? No. I lost it. I closed that window, right? But you can encode like real images and then work with them, so you can have a corresponding feature for like a real person, and then mix with other person, mix them sort of visually with someone else. Okay, right. So let's that would be this category. So this I'm getting into a category of questions which are really sort of open-ended. So like describe a GAN as a two-player game. I will probably be able to figure out like 4 possible answers and then ask you about that specifically in the first bit of the test. But I think most of these actually open up better for like a for the open-ended questions in the test. And similarly, this follows in this next category, where we were talking about 3 different techniques: pix-to-pix, style transfer, and deep dream. And it is quite feasible that in the open-ended bit of the test, I will be asking about one of these techniques, and I will be asking you to sort of describe it in some way. And so I guess I would like to start with the pix-to-pix. Could someone describe pix-to-pix as a translation? And what do I mean by that? I think Stuart, you are already like in the middle of answering it here, maybe. Mm-hmm. So what is necessary to have when using a pix-to-pix? What sort of data set you need to have?
You kind of need two versions of every image. So you need like the I guess like the raw image, and then maybe like a segmented image, which kind of says which bits are the car, which bit are the road, or
Yep. So basically that means like having a data set with paired data. So you have two domains and you have some paired correspondences between them. So 1-to-1 always. So we didn't talk about cycle gun, but that one is like the one to it, which breaks this with some magic, and then you don't have to have any correspondence there. Okay. Okay, that was roughly about pix-to-pix. What about style transfer, and why does it work? Why does it work? How can we sort of why does the style transfer? Why is it possible to separate something as content and style representation of one image? How could we do that? So how can we separate a style content and the content representation of one image and then a style representation of one image?
I think it's kind of due to the fact that styles and the content exist on like different detail levels of the image. So if you kind of think about back to like these convolution layers, you have like a convolution neural network like at the beginning, when you have like the first convolutions kind of encodes like the details of the image. Kind of as you get more and more convolutions, it kind of gets more and more like the higher level concepts of the image. I
Awesome.
think you can
That's
separate style.
That's exactly that. Great. Okay. Yeah. So it's a sort of link which connects like our third class or something with the sixth advanced class. And there are some bits which were like it's a bit more complicated. They are using some for content. I think they're representing like with one particular layer, and then the style they're sort of using all of the layers, and then maybe using some different function between the comparison of those features. But it doesn't really matter. What I will be sort of interested in when talking about style transfer is exactly this concept of being able to sort of different detailed layers. That's a nice way how to put it. Okay, so if we want to transfer styles, how would we edit the input image? This bit. So let's say we have a way how to maybe extract from one image its content and then from another image its style as features. How would we edit some other or maybe one of them input image to get more of that or that, like more style in that direction or more content in the other direction? Okay, I think I just think activation rates was something like neural net hacking that I was sort of mentioning at some moments, but this was a little bit different. So what I mean by this is, or what I'm pointing at with this question is that the concept is a little bit different from all the other previous techniques, because we are no longer editing a network with some image data. We are on the other way around. We have a fixed network somewhere, and then we are editing the input image to sort of change something inside that network. So it's a little bit like a flip of that concept of having a bunch of data, image data, and then training a network with it, but rather doing it the other way around, having a solidly trained network and then editing images with that. I guess. Okay. I mean, yeah, I agree that we didn't really go too deep into that, but like, roughly speaking, we have some features which were extracted from a target style, and then some features which were extracted from a target content, let's say, and then it doesn't really matter at which layers we are comparing with what with what, but we are the important bit there, the important shift from the previous methods is that we are editing this original input image and iterating to kind of make it to fulfill some task somewhere in the network. Okay, which sort of brings us to the last technique we talked about, which is the deep dream technique. Would anyone want to talk about how deep dream works in sort of whatever terms?
I guess it's a bit like what you were just saying. You're kind of you're choosing a particular part of the network and manipulating the image to maximize the activation in that network.
Mm-hmm.
So I guess the kind of the famous one is like altering the image so the dog feature extraction within the
Pop is like
the network is optimized, or or is maximally fired, for want of a better word.
Yeah, very well done. That's what I was pointing to. Yeah, so I like these two sort of techniques because they are sort of really flipping all of that. I mean, by now both of these methods are now sort of established as, okay, this is the standard way how to do star transfer and deep dream, but I still think that it's a bit like interesting in terms of an idea that you can then try out later as well. Yeah. Okay. Let's move on then. Unless there are some questions from this. Let's move on into sequential models. So this would be today's lecture. So I guess it's a little bit more raw, but let's still see. Could you describe what we want from the sequential models as compared from with any other models that we were talking about before?
I mean, a sequential model has the concept of not even necessarily time, but just like the one element of data is dependent on the previous.
Mm-hmm.
So like text is a good example where like one letter in a given sentence is very dependent on all the letters that are before it.
Yeah. Yeah, exactly. So somehow it's conceptually somewhere similar to the way how we were treating, like how we were maintaining locality in the data with convolutions. I mean, like in theory, you could even replace that. You could have some convolutions, and there is like, if this was a block of data which is coming sequentially, there is some amount of information here which is maintained and sort of kept next to each other. But the main difference is that we want these models to somehow encode that sequentiality by design. We don't want it to sort of have to work really hard to be able to get this information from it. We wanted to include in the design. Okay, and how we do it is exactly what we were sort of saying, is that we have these recurrent feeding arrows that are sort of keeping some information in that model when going through new new samples, new time samples, I guess, new frames, I guess. Yeah. Okay. It's a long class today. Right. So the units in the sequential models. So I think the first one that we were talking about, this recurrent neural network unit. I think this one is more or less very similar to the neural to the neuron that we would have in fully connected neurons, neural networks. The only difference there is that it also sort of keeps the information that it would be feeding to the output, but also it keeps it to itself. I think it's I don't remember the exact operation that happens inside. I think it might be added to the new input or something. But we are sort of so this one is more or less similar, with the exception of having some loop which is sort of feeding back. Where it gets even more wild is this other type of unit design, the long short-term memory units, and every block, every single unit in this block is sort of like a combination of 4 large operations. I will not, like, I don't even remember everything that happens there. One of these blog posts has a really nice way how to sort of explain it in an animation and sort of in a few paragraphs of text. Roughly speaking, there are a bunch of gates which are sort of which are using some values, some parameters, which figure out what to remember and what to forget from what we are feeding in from the last sort of from the previous frames, from the previous instances of the same unit, versus what we are sort of keeping or forgetting. And the other gate is the stuff which is maybe filtered out from the input, and then something which is then added to the output as a classification. So anyway, this LSTM unit is more complex than something like a neuron, but the RNN unit is more or less more similar to that. But in both of these cases, they have this this information which is being fed through that, sort of kept in the same unit. So yeah, they are both different, but this one is more or less more similar to the neuron. Okay. Okay, perfect. Okay, so the last 2 questions I could sort of figure out is for this lesson is to talk about the way how to represent text data and how to represent music data. So could someone explain to me how to sort of vectorize or encode some text as a dataset? That's
Yeah, I guess the one hot vector approach is kind of it's putting it in a given alphabet. So I guess text is a simple example where it's one of 26 letters or numbers, and so then that could be I guess a 26 1 by 26 vector.
What about like encoding words? If we had a
not so sure about
that. So it's more or less similar, except in text we have some like limited amount of almost classes. Like every letter can be considered one particular class. So we have fixed size of those basically. fixed space. We have a finite amount of letters. The same way, more or less, if we take a text dataset and cut it into words, we can create a dictionary for words in that dataset, and we can also just label them with with these 1 hot vectors. It becomes a bit more tricky to everything else we were sort of talking about in the rest of the class, because if you release that model, you have to give the people who would be using that dictionary to sort of decode your predictions into words and encode your new words into their sort of representation. So yeah, but it's a bit more tricky, I guess. But yeah.
So would you kind of effectively need to encode every word in a given corpus that could potentially come up?
Exactly, and you would even probably need to have like a sort of this as one word, where you would be if you encounter anything that you don't know, you would probably just encode it as an unknown sign. And I mean, that allows you to sort of have to have the model not fail when it just encounters a new word which it wouldn't see before. But it's weird. I think I might I don't know if you have the same thing on your phones when you're writing a message. It's sort of suggesting next words. I got at some moment I was writing a message and it was predicting to me like this sort of character. So it was maybe a older version of the code or something, or maybe they didn't just like erase it, but it was predicting an unknown sign, which is a bit funny.
That's so funny.
Okay. Yes, yeah. There is a lot in NLP, natural language processing, that we didn't really go through, but there is a lot of like stuff like word-to-back conversion. I'm losing my voice, Jesus. Okay, so before that happens, what about the music vectorization? Or encoding?
I guess the first step is representing the sound file as a spectrogram.
Mm-hmm.
Yeah, I think that was it.
Mm-hmm. Yeah. So okay. So yeah, spectrogram representation is one way to sort of treat signal data. So I have seen spectrograms being used in various places, not just music, but even like signal coming from some seismic measurements of I don't know, volcano activity or something, and that can be sort of encoded into a image representation, and then it's even more than just it doesn't correspond to one value in the original sequence, to one column of pixels, because for example with sounds you have like 44.1 kHz, means that a song is encoded with 44,000 values per second, and so that spectrogram representation would be really long and redundant, basically, because all of those values are more or less the same. So what happens is that there is some sort of compression. I think it looks at some intervals of music and sort of compresses that information in time domain, and then also it converts the there is a lot of math behind this, which it takes a signal and figures out what types of frequencies were originally like sinus and cosinus. This particular signal could be decomposed as. So this column of different sort of values is telling you that maybe there is a lot of low frequencies and some amount of high frequencies somewhere. Let me see an image. Where this sort of like corresponds to a band, which is telling us that there is a lot of activity of one particular sinusoid function, let's say. I mean, this is too complex. I also didn't go into this too much in the class, so it's just a sort of bonus, I guess. But do we have something like that? Right, maybe this is sort of similar to that. So every signal, every waveform like this could be sort of, it can be reconstructed as a combination of different signals, of a simpler form of signals. And so we are sort of decomposing some complicated signal somewhere into its components, and then every value here is sort of one of those components. Yeah, which is, yeah, anyway, it's not really that important in his. Yeah. Yeah, check other sources as well, please. I could have gone a bit more about this in the class, I think. So I guess what we care about on the machine learning end is that we have somehow converted a music signal, which has been really a lot of values in the time domain, into something which is fixed to a block of data. So it has less amount of time steps, and also it has some fixed number of these bands. So we have a block of data which is kind of really more standardized. So it's something that we will always know that it is coming with like some amount of numbers by a vector of 1025. Oh, yeah, this particular number depends on the settings of the FFT, but we sort of converted a sequence of just numbers, which was really inefficient in a way, into a efficient compressed representation like spectrograms. And one more trick there is that we can also convert it back from there. So this FFT and then inverse FFT, it's not it's lossy because we are sort of losing some amount of information, but we can live with that. And this becomes more or less similar to the way we were representing the text data. So the spectrogram is more or less similar to the dataset we had here, except that these were one-hot vectors, one hot represented vectors, whereas this is full-on vector with a lot more values. So there is not just one, but there is a spectrum, like there is a distribution of those values across the columns. But yeah, please do also check other explanations. I think there will be. Yeah. Okay. Let's see. I think we more or less went through everything that I prepared as a general area of things, or like a topic that I could be asking about. Do you have any sort of final questions or any details that you would want to ask about any of these parts? Okay, so it seems like maybe no, or maybe that you are all tired. I think we were going for like 2 hours already, right? Yep. So, and now it will be time for another pause. Okay, but let's bring this class to the end. How prepared do you feel for the exam? Is anyone worried about it, or or okay? Yeah, I think.
I mean, it's today.
Uh-huh.
I'm guessing today was kind of what we should kind of expect from the exam in terms of like the sorts of questions and the style of questions.
So what you should like today, it was more or less going about the topics. The questions themselves will be more in detail of something, like not not the unnecessary details, but sort of similar topics, but more specific questions. So it will be, I think, easier to answer, I hope. yeah, it doesn't really matter. Like in the open-ended questions, you can use sort of whatever terminology. I will try to decode that. Okay, cool. Yeah. I hope this. Yeah, I mean, I remember my own courses, and it sometimes happened that the whole class was like bizarre. There is some magic terms happening again and again. So I'm like, what is this nonsense? What is all of this? Like, what does it mean to do this operation? What the hell? And then finally, in the moments of like practicing for the exams, I figured out like, oh my god, all of these things, they mean just this one thing. It's actually simple. Oh my god. And then yeah, I hope that your practical kind of studying for the exams will hopefully bring all of those terms which are flowing somewhere in the air into more like refined domain of like knowing these topics roughly. So yeah. Okay. Yes, to answer this. Yeah, I will not be talking too much about the interactive ML. So I will ask Rebecca if she has some questions that she would like to ask. But it might, yeah, it will not be the full-on. Yeah, there will be questions from other domains as well. Where I can be asking about some interactivity is probably in the autoencoder and GAN side of things, because even in our practical session we had some experience of working with some like interpolations. I don't know exactly what I will be asking yet. I have to write down those questions, but yeah, you can expect some questions about interacting with autoencoders and GANs, and maybe what is the difference, or maybe what are the cool things you can do there. Okay. Okay, so more or less we have finished with today's recap. So this is the end. I would like to I would like to ask you for some feedback, basically. I don't know if CCI or UAL in general has some sort of way how to collect some information about the courses. I think they have, probably, but I'm not sure if I will ever get to see that. So I brought up my own sort of feedback questionnaire, and I will share it with you. And I would like to sort of ask to just fill in this form. All of it is anonymized, so basically I will not know who said what. Also, I tried to make all of those questions more or less like well, yeah, the whole reason for this feedback is to be able to get some information about the course. So maybe figure out which parts of the course were lacking in some terms, or which ones were maybe too detailed that it didn't really need that. So I tried to like have some questions about that, and maybe also leave like a last open-ended question to just leave any comments that you would like to do. And so I would like to ask all of you to just have a go at this. Some of the questions are like you have to pick a number there or something, but some of them are just like optional. So if you don't know how to answer something, it's fine also not to leave anything. And in this questionnaire, please also include any like critique. I will not know who critiques what, so it's you're sort of safe. But on the other side, I also like all of those questions are it's nothing personal. I sort of want to perfect this course over this over this teaching. So if I'm teaching any bits of similar courses like this, I would like to have a real feedback to sort of know, okay, what needs to be done more. Yeah. I mean, on one part as well, I would like to have more more weeks. So yeah, and more time also to prepare everything. That would be nice. Okay, I will send, because I don't think that maybe not everyone is here now, so I will send this link again in the Slack. But yeah, please do fill this in. I will not share it with my CCI overlords, so feel free to leave anything you want in there. Okay, cool. So I think this is everything for the class. For this recording I'm doing right now, I will put it together. I think there were 2 bits separated by the pause, so I will put them together and then upload it somewhere and leave it private. And so the reason is that like I feel like an idiot when I'm listening to myself, whenever I'm listening to myself on any of those recordings, and so I'm sort of trying to protect you from that. Because yeah, it's okay to like, yeah, it's a joke, right? And yeah, also I think this session was kind of for you and only for you in this class, so it's okay to just keep it private. And it might eventually help with some practicing, because you might like have to recall what the hell was he meaning with locality here, right? So yeah, cool. Okay. I think I can sort of collect various interesting resources I stumbled upon when I was going through this. And maybe some of them would be linking to some blog articles, and maybe some of them would be linking to some like Colab notebooks. I found that a bunch of people are sort of collecting just links to Colab notebooks, which are showing like a really new state-of-the-art research thing. And so that is really nice, because you can then load that up, just use it for whatever, and then see if it plugs into your own pipelines somewhere. So I can make a list of that, and maybe I also know like some resources where there are 2-minute papers. Is like a YouTube channel where they are sort of talking about new channels, and so I mean new models which are coming into like computer graphics domain. So that would be me too. Also, he has an awesome accent. I think he's Hungarian or something, maybe, right? Anyway, so I will try to collect these resources and maybe add them as like one last bonus slide presentation at the end. I don't know when I will get into that. It might take me some time, and it might be out after the class, but maybe it's okay, because like it will not be really involved in the exams for this class. Okay. Well, so this is I think everything. Let me stop all of these, and good luck with the preparations for the exams. If there are any last questions, you can also still send me some messages through Slack or on my email. And if I am, if I find some time, which I will try to, I can then answer them. Cool. Thanks.